Greetings and welcome wherever you are and whenever you have come to this virtual talk for FACT 2021. I welcome you. My name is Joshua Kroll. I'm an assistant professor of computer science at the Naval Postgraduate School in beautiful Monterey, California. I'm here to talk to you about traceability, a principle which goes back a long way in software engineering and has recently found its way into a number of AI ethics principles documents and policy documents that we'll discuss, and that I think of as a way of operationalizing the value of accountability in computing systems. I want to start, though, by situating those computing systems in the broader context of engineered systems generally. When you talk to engineers who work on other kinds of systems, they will tell you that they have tools and techniques and procedures for assessing those systems and determining that those systems are fit for purpose. And while the systems may not be perfect, at least they're amenable to control and amenable to some sort of assurance. And those techniques exist in the computer science literature as well. There is an enormous amount of work on assurance for computer systems. And yet, when you talk to computer scientists and computer engineers and software engineers especially, you find that they do not feel that they have the tools, techniques, and procedures available to achieve that same level of control and assurance in the systems that they are building, or the same level of assessment of those systems as fit for purpose. And yet, we see that those systems move into the world and do important work in a way which is perhaps undermined by those systems' lack of assurance. I think this is well underscored by the example of voting electronically. If you think about direct record electronic or DRE voting machines, they're just computers that run software which take input from voters and turn it into vote counts. That input might come from a peripheral device like a touchscreen or a keyboard, but somehow it is turned into a vote count. And because it's just a computer, it just runs software, and that software can do anything you want, including something other than counting votes. And that leads to problems with the trustworthiness of the system overall, as it did in the United States after the 2020 presidential election, where vulnerabilities, real substantial vulnerabilities in these machines for undermining their ability to reliably and accurately report vote counts with integrity was misrepresented to cast aspersions in the direction of the integrity of the election as a whole. And while those representations were exaggerated, it was the case that they did lead to a number of recounts, recanvasses, and audits across the voting system in that election. And those activities led to a situation where the outcome of the election could be validated. And that validation happened not despite the vulnerabilities in the DRE machines, and it happened because there were records of how the election system operated, how the election system was built, and where the design limitations were. And so the combination of records and design knowledge provided the tools necessary for auditors to move the system forward and make it actually function. And that brings me to our core idea, which is traceability, the idea that you should have records which allow you to trace not just how a system operated, but why a system operated in a particular way and what design decisions led you there. So if we amalgamate a number of definitions of traceability from the literature together, we find that it refers to a kind of targeted transparency around systems that describes the scope of the system, what data the system touches, what the system is meant to do in terms of function, what the inputs and outputs of the system look like structurally, but also transparency of the design decisions and the origins and the development decisions that were made in bringing the system into existence. And that transparency isn't just an end in itself. It exists for a purpose, and that purpose is to provide relevant stakeholders of the system with an appropriate understanding of the operation of the system, but also its provenance, also where it came from. also why it behaves the way it does instead of some other way. And so traceability is not just about transparency. It's more than transparency. It's more than saying, let's just, you know, look at how the system works somehow, pick your favorite metaphor, opening the hood of the system and looking underneath to see how it works. But really, it's about relating those disclosures, that transparency, to the reason that you'd want that information in the first place, the reason that you need specific information, and that tells you what information is valuable to know in order to understand that. And what gives that value is this idea of facilitating understanding of the system. And the purpose of that facilitation of understanding is to hold people and organizations accountable, responsible for the behaviors of the system. So we can think of traceability as a kind of demand for documentation, but that documentation is broader than just how do I use the system or what went into the system or what is the architecture of the system, but it covers the design methodology, the lifecycle process, any data or other infrastructure on which that process rests, and also pre-design activities like the formulation of the problem or the setting of the goal for the system are covered by this demand for documentation. So it's sort of a full provenance of the system's backstory, it further encompasses the system in operation in most definitions as given, and also most definitions describe traceability as a relationship between transparency and oversight and accountability, and that function of holding the system responsible through making relevant stakeholders not only aware of but understanding of the system as embodied. So traceability, as I said, has a long history in the software engineering literature. It also has a pretty robust history in policy and AI ethics documents, especially promulgated by governments. So it's promulgated in a number of United States federal AI policy documents, probably most prominently in the Department of Defense's AI ethics principles, of which there are 5, and one of them is traceability. But it shows up in a number of other places outside the US as well, including in guidance from the European Union's high-level expert group, in transnational guidance from the Organization for Economic Cooperation and Development in the United Nations, and even in non-Western policy principles like China's governance principles for responsible AI. And if you dive into these principles and try to boil them down to a set of concrete requirements that you could implement to say, yes, I have really done what the policy guidance says I should do, well, those requirements are numerous, and they sort of follow that definition that I started with, which is to start with transparency of the system. But not just transparency of the system, transparency of the provenance of the system, the sort of origin story, the backstory of the system. So just disclosing things about how the system works or how the system worked in a particular case, that's not enough to satisfy traceability. Traceability is about disclosing the right information so that people understand things, and disclosing that information for the purpose of connecting it to subsequent assessment. And to that end, that understanding is not the same thing as explainability. It's not the same thing as mechanically saying, I can get from these inputs to these outputs. It's saying, why does the system go from the particular distribution of inputs it takes, or the particular set of inputs it takes, to the particular set of outputs it gets? Why are those the input-output relations of the system, and why does the system not embody a different relation? And then there are other components to these requirements, like the requirements, because they support later assessment, need to be evidentiary in nature, so you can't just sort of spit them out in a way that's not verifiable. And finally, you want the system to be reproducible in the sense that if you can trace the origins of a decision, you ought to be able to reconstitute that decision entirely from any component part of its provenance. And as I said, all of that feeds back into this notion of auditability, or the ability to make assessments about the system. So I think of this a little bit as a kind of accident reconstruction problem, right? When you have an accident of a vehicle or some other engineered system, you want the parameters of the system at the time of the accident to be somehow amenable to review. That means that the information that an investigator needs is available in some form. It's sufficiently informative for the investigator to do their job, and it's faithful to reality. It's not just made up or faulty data or something like that. It actually represents what really happened. And if we think in that frame of a sort of black box style recording device, then we are reminded of the famous quote of the noted critic Jay Seinfeld, who argued that if the black box is the only thing that survives the crash, why don't they just build the whole plane out of the black box material? And well, that's not reasonable in many applications for vehicles, for planes, for ships that do have something like a black box or a data recorder that is used to provide this kind of accident reconstruction. In the world of computing, we certainly can build the whole plane out of the black box, and traceability is telling us that as a matter of ethical system development, we perhaps should be doing that. And there are even, I don't think that's quite what was meant in some earlier calls for thinking of algorithms in a black box setting. Something that I'm interested in as a computer scientist is, how would we take this call for building a more robust tracing of how a system works and why it works that way into something we can actually build? And so in the paper, I look at ways that we can meet these requirements with tools that we have in the toolbox for computer scientists. I think some of the biggest tools come out of discipline around the software lifecycle and tooling around the software lifecycle. Things like continuous testing or version control, or tools that allow us to ensure that systems are reproducible, whether those are reproducible builds for software artifacts, reproducible training paths for machine learning models, or provenance systems that allow us to track system state in a precise way, but also an efficient way. Because the more precision you have about the state of a system, the more data you have to carry, metadata you have to carry about the system along with actually operating the system, the more heavyweight that is. There's a huge literature in the systems community about how to do that work in an efficient way, efficient enough to deploy for a whole operating system or a whole distributed system. So that's a way of fighting back against this kind of unstructured approach to data science and machine learning that we often see in practice, where the process is just to dump all of the components into a pile and then stir them around in your Jupyter notebook until the answers look right. Another set of tools that we have available to us is structured evidentiary logging. So there are a number of tools that go back, in some cases, many decades, for maintaining the integrity of data over time and verifying the relationship between data in different states and verifying the relationship between data as it is transformed by a program from one state to another state. Some of those allow us to make commitments about what is in the data and how the data should behave between those states, and also to provide some kind of tamper evidence. Were the data changed between this state and that state? Can we rely on their integrity? Can we rely on how they've been moved from one place to another? There are also ways of building systems such that we know that those records are correct by the way they were constructed. And we even see these tools being used ostensibly in practice, for example, in DeepMind's verifiable data audit tool. You see a sort of correctness by construction approach to the training inputs given to a deep learning model, which is kind of a neat approach. All of these ideas really are encompassed in the world that is known by the buzzword of blockchain. But as a computer scientist, I firmly refuse to call a system where every object has a parent, but there's no rule that says that a single object can't be the parent of more than one other object. A chain, it is a tree of blocks, and that is what I have shown here. A final suite of techniques that we have for traceability relate more to policy. So when do we document things? How do we document things? How do we know that the documentation is correct? There are many tools for this, right? A checklist, a simple checklist is a tool. Here I've shown a checklist from the Apollo 11 mission. And checklists can be incredibly powerful. They can also be documents that lead to a kind of box ticking approach or a compliance approach that says that things are not as the checklist says they are. It's just that we did the right work so that we could get the box checked on the checklist and move along. And so that's a bit of a risk when you see more detailed kinds of structured metadata documentation like model cards or data sheets. And the other important thing to remember about documentation is that it doesn't change organizations on its own, and also that there's no inherent reason why the stuff written in the documentation reflects how the system actually works in practice. In fact, having worked in the software industry, I can say that it is definitely a meme in the software industry that some documentation may be out of date. It is a joke that engineers pass to each other, essentially to say, go figure this out for yourself, because you're not going to learn how it works by reading the documentation. And in fact, documentation as gatekeeping is a quite common form of engineering culture, sort of hazing an engineering culture. So that's an interesting problem with relying on documentation as a tool on its own. Fortunately, there are technical tools that might help us get around that, and of course, policy tools that might help us get around that. In terms of that connection to oversight and accountability, we can think about how to deploy documentation in a way that makes people responsible for the contents of that documentation. And that is a feature of many other kinds of management tools in the critical safety engineering community. So in thinking about requirements and thinking about the tools we have for meeting those requirements, we have gaps between what we need to do and what we can do. And the paper spends quite a bit of time on what these gaps are and how we might fill them in with new research or new adoption of tools and techniques and procedures, and whether that would be enough. So adoption is a gap. We have a lot of tools. We know a lot about how to solve this problem, but those tools and techniques and procedures just don't get used in practice. And the question is, why not? Are they actually insufficient? Do we not somehow understand the problem in exactly the right way? What is the reason for this is a big open question. A second big open question is around treating understanding as a human factors problem. So when we talk about transparency or we talk about explainability in the technical literature, we're often not talking about the kind of situated understanding that traceability demands. And a question of what do you need to get that understanding is really critical and really underexplored. A final open question that's incredibly important is about standards, having standards for assessment of systems, evaluation of systems, and testing of systems. Right? What evidence do we need to know that a system is behaving in a good way? How do we actually make those assessments? What is the standard that should go into that auditability, that investigation activity? That's something that exists in other engineering disciplines and doesn't necessarily exist in every aspect of computing systems. And so to that end, I want to put up this diagram from Nancy Levison's amazing book, Engineering a Safer World, which is about applying systems engineering thinking to safety problems, which sees control of a system as a kind of overlaid second system that helps manage the first system, going abstractly from policies and laws and all the way down to the operation of individual components and the activities of human operators. So to conclude, traceability is a value that we should care about, a principle that we can use to operationalize a more final value, a less instrumental value of accountability, because it shows us when transparency is valuable for that governance process, for that accountability. Traceability is a very achievable property. It's much easier to measure and has a much closer relationship between measurement of process and measurement of outcomes than something like fairness or privacy, which could be very abstract and very even contested among different stakeholders. And with that, I will be happy to answer your questions during the Q&A or by email. Thank you very much for staying all the way to the end of the talk.